Hello everyone, welcome to the ATAR Notes Prelim Chemistry April lecture, provided to you by, of course, ATAR Notes. So I'll introduce this lecture by starting with a little bit about myself. So my name is Thamika. I graduated from North Sydney Boys in 2022 with an ATAR of 99.3, and I got an HSC chemistry mark of 97 out of 100. Right now I'm studying medicine all the way in Queensland, so pretty long way, but I enjoy it quite a bit. Some of my hobbies are, well, the first two I picked up after the HSC, playing Bed Wars and Valorant, and I also like to play piano quite a bit. So that's a little bit about myself, and now just a quick bit about ATAR Notes. So since 2007, we've been offering heaps of free resources to make sure students just like you can thrive in their studies. We've offered free lectures just like this one since 2015. And these free lectures are in line with ATAR Notes' mission to help students as much as possible. And we have tons of free resources for you, as you can see on this slide. So here are just a couple of the things that we offer: study notes, lectures, videos, newsletters, ATAR calculator, and study guides, and heaps more. So you can find pretty much everything at atarnotes.com. If you want more info as well, you can check out the info doc under the resources section of this lecture page. And we have free notes, videos, free guides. And if you have any more questions after this lecture, the best place to go is to the online Q&A section, where either current or past students just like me can answer your questions. And if you're looking for even more support, we've got you covered. So here are a couple of the premium resources that we offer. So for low-cost group and private tutoring, we have TuteSmart. We also have printed study guides and online access to study resources with Ed Unlimited. And finally, I'd like to thank all of our partners, as you can see on this slide, for helping us make these lectures happen. So with that out of the way, let's get into the lecture. So here's a bit of the overview of what we're going to go today. So first of all, we have an intro and some general study tips on how to approach chemistry as a subject, especially going into HSC chemistry and continuing and finishing off your prelim year. And we also have a little bit of a review of Module 1, and then we go through and we try to finish off Module 2 by the end of this lecture. So it's pretty crammed, and the main important thing to know about this lecture is that we're not trying to get you to know every single little detail about every module. We're trying to get you prepared when you're going into class. We're trying to get you prepared and understanding the general concepts about Module 2. So that's what you need to get, and that's our goal for this lecture. So with that out of the way, let's get into the lecture. So some general information. So before you start studying, you need to know what you're dealing with. So chemistry, finishing off HSC chemistry, I felt like it felt very close to English, in the sense that you really need to be aware and understand what you're writing and how you're trying to communicate the point that you're trying to get across. So you need to have strong logical reasoning. You need to have a good mathematical base. It's not too hard. It's going to be mainly algebraically based. So we'll go to some of the math questions that we're going to be going through later in Module 2. And you need to be able to clearly express what you're saying. So have a clear, succinct language use. And chemistry is always about building on your weaknesses. So this is something that I really focused on in HSC chemistry. I'd always focus on where my pitfalls were, and I'd always try to improve on this as my exams and past papers progressed. So when you're tackling the content, it's very important to use different sources of content so that you can, improve your understanding. And what's very important is your sense of understanding you should be focusing more on your sense of understanding compared to your ability to memorize. So I really believe that memorizing chemistry won't help you in the long run, especially when you have to remember a lot of stuff in the future as well. So you have to remember all the information that you're learning in preliminary in year 11 all the way into year 12. So understanding the content is what I really believe will help this process of remembering. So understanding the content, you'll draw relationships between all the different pieces of content that you learn, and it'll all fit into this big one puzzle piece. And that's what really clicked for me in HSC chemistry. And so I really believe that this is the method to maximizing your output in chemistry. And if you want to help yourself learn better, you can break down the concepts into smaller and more simpler concepts, and then when you put them back together, it'll all make sense. So when it comes to doing your in-school exams, this follows through in the HSC year and your year 11 year, your school should be prioritized over whatever the textbook or something says, because in reality, your school is what's going to be giving you your marks. So you want to always focus on what your teacher is saying, what your teacher is teaching, and what your school is teaching you compared to what your textbook is. Because as I said, for your school marks at least, your school is going to be the one that's delivering your marks. So you always want to be looking over your teacher's exam comments. So whatever your teacher said you need to do to improve, follow up on that and make sure you build on your weaknesses. And also make sure to communicate with your teachers. So your schools, just like my school, our school had very specific ways on how we should communicate our information. And so our relationship and connection with our teachers allowed us to, fulfill this like extra requirement basically that we had, because we had to communicate our information in a certain way for some topics. And so communicating with our teachers allowed us to understand this and not lose marks on these sections. So you make sure you do this for your school exams. And doing questions. So a lot of people, including myself, when initially looking at a hard question, we tend to avoid it. We tend to see it as, difficult, or, we tend to see it as difficult and then avoid it, right? Because we're scared of getting it wrong, or we don't know where to approach it from. Well, the best thing to improve with that is to just do it, basically. So you're only going to realize if it's hard or not if you end up doing it, and you're only going to realize where you make mistakes if you actually do the question. And this is something that I learned the hard way towards the latter end of my HSC year. Doing questions is very important. So you need that practice, and you need that exposure to different types of questions to make sure that your exams are easier. So I really noticed the benefit of this in my actual HSC, where after doing a lot of past papers, I realized that all the questions that I got in the HSC were like, I've already seen a type of question like that before in one of the past papers that I've done. So doing questions is very important, because when you go into the HSC, then you're never going to be experienced, or you're never going to see a new question where you have to think, oh, I've never seen that question before. If you do enough questions, you'll have seen a variation of all the types of questions that you'll see. And there's basically 3 different types of questions that you'll come across. So multiple choice, which is like the first 20 questions that you'll get. And then you get short answer and long response questions. So when you're looking at these 3 things, in the new syllabus, long response questions have become a lot more prominent. So 8 to 9 markers might be there in your HSC exam. It's less so common in your preliminary exams, but it's a lot more common, and you should be able to answer these and should be getting prepared to answer these in your long response exams. So short to mid-length responses are now a lot more common, and 8 to 9 markers, you really need to be able to, as I mentioned before, have succinct and clear language so that you know that you're getting your point across effectively. So you don't want to be rambling on about stuff that's not relevant or is skirting around the question. You really want to unpack the question and then answer the different keywords, or hit the different keywords of the question. It's in that sense, it's quite similar to English. So, but the MCQ is quite straightforward, and then it's just very simple calculations, or you just need to read the question and understand what it's saying, or maybe it's just testing your memorization ability. So I did say that you need to be able to understand things, but some stuff requires some level of memorization. So the colors of the flame test, for example, that stuff, that it's pretty memorization based, as it's quite hard to understand it per se. So yeah, simple data interpretation, memorized facts and calculations, that is what MCQ is mainly composed of. And to a certain degree, the MCQ can be quite difficult, because if you're exposed to things that you've not been made aware of. So say you forget a fact and the question is testing you on the fact that you forgot, it's going to be quite hard to get that question right. So in that sense, it could be quite difficult. But in most cases, if you have a general and good understanding of the content, and if you've done a lot of questions, you should be very good. And the next important thing is, when you're doing your exams, I highly recommend that during reading time, you skip the multiple choice questions and you go through the short answer questions, because in my opinion, at least, doing the multiple choice questions during reading time has a very low yield, because it's better off for you if you look through the short answer section and see what content they're testing, so you can prepare yourself for that content. Because either way, even if you solve the MCQ questions, there's no way that you can prepare yourself beforehand for them. You have to do them either way. You have to do them on the spot, right? But for short answers questions, you can, during the reading time, say you come across a 9 marker, you can in your head start planning how you'd attack that 9 marker, how you'd structure your response, what keywords you're unpacking. So reading the short answer, in my opinion, is a lot higher yield than doing the multiple choice during reading time. With that said, time management is also very important. Make sure that you're not skipping a 9 marker to finish off the exam. Probably see in which areas you'd so if you're not going to finish, you need to see in which areas you need to move on to get the most marks. In that sense, time management is quite important. So there's for short answer, there's a lot of question types, and for most short answer questions, it's just the content, and if you know the content, you're pretty well off. But the thing is that it's also quite easy to lose marks here. So silly errors like calculation errors and, not explaining a question or like, restating the question instead of actually answering the question. It's where most people lose, 1 or 2 marks, and these tend to add up as your exam paper goes on. So make sure that, you actually answer the question. So in that process of unpacking the question, especially for, long response questions, you definitely want to make sure that you're unpacking the question, but don't just define what the question says. You actually want to answer the question, right? So you unpack it and then you answer it. A lot of people forget to answer it and they only end up unpacking the question. So you want to make sure you get both steps done. And so, yeah. Like I mentioned before, long response questions are where chemistry becomes quite similar to English in the sense that you end up, it's like you're writing mini essays. So yeah, for long response questions, I highly recommend, and this is why I highly recommend doing the short answer section during reading time. Because when you get to the long response section, you can, it's like reading time in English, basically. You read the question, you try to unpack the question, you're trying to find which areas or which content knowledge are they trying to test me on. So you think from the marker's perspective as well. Then you unpack the keywords, make sure that, you're including the keywords in your response and you're actually answering the question with the keywords that they want you to use. And so, yeah, that's how you basically get marks. And if you know the content that you're asking for, it's very easy to get like let's say if it's a 9 marker, if you know what they're asking for, if you unpack it properly, it's very easy for you to get 7 and above out of 9. So if you know what you're doing and if you employ these techniques properly where you unpack the question, you look at the keywords, make sure you use the keywords in your response, make sure you answer the keywords, and make sure you're actually answering what the question is asking you to answer, then you're very well off. But the thing is, if you're not prepared, if you don't understand what's happening, and if you're trying to wing it, then this is where like a lot of people lose marks here. So like getting a 3 out of 9, you're tanking 6 marks there. So yeah, 6 marks is a lot, especially when you have other silly mistakes that you'll probably make as well. 6 marks is a lot. So long responses is like a make or break it moment for a lot of students. And yeah, and the flow of your long responses are also quite important. So for my long responses, I always use subheadings. Subheadings not only does it make it easier for you in terms of structuring your response, it also makes it easier for a marker to actually understand what you're doing. So a lot of people might end up writing it in a big, like one block. So you don't want to end up writing your responses in one big chunk of like writing basically, because it's a lot harder for markers, because when markers are marking your writing, they're trying to look for the keywords as well. They themselves unpack the questions and they're trying to see if you've answered the different parts of the question and if you've displayed enough content knowledge to give you full marks. So if you write in one big chunk, it makes it harder for the marker to interpret what you've written, right? But if you write it in subheadings, it kind of inherently shows that you've unpacked the question and you know which parts, like how to respond to that question. So your long response questions, if you use subheadings, not only does it make your answer more organized, it also gives like this inherent idea that you know what you're doing and you're pretty confident in your answer. And it makes it easier for you to get your knowledge across and get your answer through. So make sure to subheading your answer where appropriate, obviously. And also try to include diagrams. So in chemistry, especially when we're going into HSC chemistry, you'll have learned a lot of chemical equations. And for long response questions especially, make sure you always include at least 1 or 2 chemical equations. It just makes your answer a lot better, and it also what it does is it basically boosts the quality of your answer. And so yeah, a lot of people, especially if you're aiming to get quite high in your chemistry paper, make sure you use chemical equations, because it won't stop you from losing marks if you make a mistake, but what it does is it increases the quality of your answer, if that makes sense. So those are long response questions. And so this is kind of what the year 11 course structure looks like. So we have module 1, which is properties and structures of matter, which you guys would have already done in term 1. Module 2, you have introduction to quantitative chemistry. So in my opinion, in year 11, module 2 was my favorite section because this is more mathematical based and more calculation based. Module 3 is about reactive chemistry, and module 4 is about drivers of reactions. So yeah, also you have 15 hours of depth studies between modules 1 to 4. So that is your course structure for year 11. Now let's explain how the emission spectra works. So this is, now we can move on to module 1. So this is an example of a question or a mid to long response question in module 1. So the question goes, explain how the emission spectra works. Use expected terminology and include a label diagram for this process. So let's unpack the keywords here. Keywords is emission spectra. And what the question is, so let's look at the keywords first. So we have emission spectra, we use expected terminology and label diagram. So we need to have a diagram. Now let's look at what the actual question is. So we've unpacked the question, we know what the keywords are, but what is the actual question? So the question is, how does the emission spectra work? So we need to explain how it works. So we need to know how the emission spectra works. So expected terminology and stuff. So for this question, we talk about the electrons being excited and then returning back to its ground state and then releasing electromagnetic radiation, causing an emission spectra to be produced. So if we're now looking at the answer to this, we'll look at this. So the emission spectra refers to the phenomena where electrons move from lower energy levels to higher ones when they absorb energy, known as excited electrons. These excited electrons immediately return to their original lower energy level, known as ground state. In the process of returning, these electrons release energy in the form of electromagnetic waves. These electromagnetic waves are then collected and processed to form the specific atom's emission spectra. So we used expected terminology here. So the excited electrons, ground state, lower energy levels, high energy levels, the electrons, and we also drew a label diagram showing how these electrons, what happens when they're excited and what happens when they go from an excited state to the ground state or a lower energy state. And we explained how the emission spectra works. So it works by, the way it works is when something goes from a high energy state to a low energy state, it releases electromagnetic radiation, causing an emission spectrum to be produced. So this is how you would unpack and answer a question. Obviously, in this case, you don't have to number it 1 to 4. You can also structure the question in a sense where you can say the emission spectra refers to the phenomena where, and you finish the sentence there by finishing off that sentence, and then you can go through the steps of how, for example, the electrons get excited and then they produce an emission spectra. So you could write this in a paragraph sense, or you could also list it out like this. Your school, it really depends on your school preferences. Some schools ask or teach their students to answer your questions through bullet points, and some schools teach their students to answer it via a paragraph. My school asked us to do it via paragraph length, and so I would structure this in a paragraph rather than numbering this 1 to 4. But obviously, the important thing here is that you unpack and hit the keyword. So we used the expected terminology, and we included a labeled diagram. So our next question, is sulfur trioxide a polar or non-polar compound? Why or why not? So let's look at the keywords here. So the keywords is polar and non-polar compound, why and why not. So what is the question actually answering us? It's answering us to identify whether sulfur trioxide is polar or non-polar, and we need to give reasons why. So this one is not a long response question because it's 3 marks. I'd consider this short answer because as long as you list 3 things, then you should be pretty well off. So looking at the answer here, first we identify whether it's polar or non-polar. So we say it's non-polar. So I'd say sulfur trioxide is a non-polar compound. That should be 1 mark in itself. Now we say, even though sulfur trioxide consists of 3 polar SO double bonds, these bonds are equally spaced apart from each other due to the compound's trigonal planar trigonometry. Hence, these polar bonds balance each other out, resulting in a compound that is overall nonpolar. So for this question, looking at this question, I'd probably say, so the first part here, right, is sulfur trioxide a polar or nonpolar compound? I would give this out of 3 marks. I'd allocate this entire sentence 1 mark because all it's asking us to do is identify whether sulfur trioxide is a polar or nonpolar compound. It's not asking us to do anything else. So there's no reason why it would be worth 2 marks. So this first sentence counts for 1 out of the 3 marks. Our explanation is what counts for 2 out of 3 marks. So I'm looking to write around 2 sentences for that. So I'd first identify that the SO bonds are polar. So that's very good as well. The fact that I identified that SO double bonds are polar is another thing that would get me a mark. So I say that sulfur trioxide consists of 3 polar bonds, but they're equally spaced apart from each other due to the trigonal planar trigonometry. So me identifying that it's polar, but it's actually equally spaced apart from each other via the molecular geometry is what would give me the 2 out of 3 marks, or basically 3 out of 3 marks. And then I'd say because these are trigonal planar trigonometry and because they're equally spaced apart, they balance each other out, resulting in a compound that is overall nonpolar. So me identifying that it's nonpolar, that's 1 mark. Me identifying that the bonds are actually, the compound actually has 3 polar bonds, but they're equally spaced because of the trigonal planar trigonometry is the 2nd mark. And then me linking that trigonal planar trigonometry to the polar bonds balancing each other out, resulting in an overall nonpolar compound is the 3rd mark. So that's how I would structure the marking and how I want you guys to look at a question and identify where the marks would be given as well. So define electronegativity and first ionization energy. why do highly electronegative elements also tend to have higher first ionization energy? So this one is 4 marks. So define electronegativity and first ionization energy. So obviously 1 to 2 marks is going to be allocated here. And then we do, why do highly electronegative atoms also tend to have higher first ionization energy? So this one, I'd say they're allocated to around 2 marks as well. And the first sentence, I would say they're allocated around 2 marks as well. 1 mark for defining electronegativity and 1 mark for defining first ionization energy. So now that I have a general idea of where the mark allocation would be, let's answer the question. So electronegativity refers to how likely an atom is to attract an electron, whilst first ionization energy refers to the amount of energy needed to remove a valence electron from a neutral atom when it's in gaseous states. So we've defined both electronegativity and first ionization energy, and we've also made a comparison by using the word whilst. Highly electronegative elements have a very high likelihood of attracting an electron. Thus, removing a valence shell electron from the atom of one of these elements requires a great amount of energy. Hence, highly electronegative elements tend to also have higher first ionization energies. So, now what we need to do is we need to make the link between electronegativity and first ionization energy. So by saying that basically if we're trying to remove an electron, and so an electronegative elements try to attract electrons, right? So if you try to remove an electron from electronegative atoms, it's going to be quite difficult. Same with, first ionization energy. First ionization energy directly refers to how hard it is to remove a valence shell electron, right? So that's the link that we need to make. If it's harder for an electronegative atom, if it's harder to remove electrons from an electronegative element, it by definition has a higher first ionization energy. So that's a link that we need to make. So I reckon this is worth 2 marks, and this first paragraph is also worth 2 marks. But obviously, I can't guarantee anything. There are cases, especially in my school as well, where sometimes where I don't understand a question, I try to unpack the question, see where the mark allocation will be. So say I don't know how to answer this question, right? But I do know what electronegativity and first ionization energy is. So what I do is I'm like, okay, so I know how to define these. I don't know how to answer this second part. So what I'll do is I'll define these two and I'll skip and I'll go to the next question. And I expect 2 marks out of 4. But sometimes the marking criteria can give this entire sentence only 1 mark. So I'll get 1 out of 4. So there are cases where your expectations don't actually match the reality. But in terms of answering the question, it's very good to try and split the question, break the question up, and try to identify where the marks can be allocated or could be allocated. So now that we've done some of Module 1's harder questions, like, short answer questions, we can go on to Module 2. So let's look at the content focus. So in this module, students are introduced to the quantitative nature of chemistry, and they must be able to identify or quantify reactions in order to make predictions about the yields of certain reactions and communicate with specific audiences for specific purposes using nomenclature, genres, and modes unique to the discipline. Using the mole concept, so this one is like the most important part and the most prominent part of our Module 2. We'll learn about this later. Using the mole concept, students will have the opportunity to select and use appropriate mathematical representations to solve problems, make predictions, and calculate the mass of reactants and products, whether solid, liquid, or gas. So, make predictions and calculate is personally my most enjoyable part of this module. So, yeah, it's kind of like, it was quite algebraically based, but not hard algebra. It's very simple algebra. And so I really like the concept of moles. And this was something that actually got me quite interested in chemistry as a subject as well. So students further develop their understanding of the universal language of chemistry. They're introduced to the idea that science is a global enterprise that relies on clear communication, international conventions, peer review, and reproducibility. So that's the content focus for Module 2. All right, now let's look at the structure of Module 2. So first we'll go through chemical reactions and stoichiometry. Then we go to the mole concept, my favorite part. Then we go through concentration and molarity, very closely linked to the mole concept because concentration and molarity is, moles are part of the units for concentration and molarity. And then we go through the gas laws, which I also found quite fun as well. So now let's go through chemical reactions and stoichiometry. So in this inquiry question, what happens in chemical reactions? Students are required to conduct practical investigations to observe and measure the quantitative relationships of chemical reactions, including but not limited to volumes of gases in chemical reactions, masses of solids or liquids in chemical reactions. So we need to be able to conduct investigations and measure the relationships of quantity between masses and solids and gases in chemical reactions. And then we need to be able to relate stoichiometry to the law of conservation of mass in chemical reactions by balancing them and by also solving problems regarding mass changes in chemical reactions. So we always need to make sure that the mass of the product is similar or equal to the mass of the reactants. So, dot point 2.1.1. Conduct practical investigations to observe and measure the quantitative relationships of chemical reactions, including but not limited to masses of solids and or liquids in chemical reactions and volumes of gases in chemical reactions. All right. So let's look at the law of conservation of mass, which you've probably heard before. So this is a practical dot point, which we'll conduct more in depth at school. But basically, the law of conservation of mass states that matter can neither be created nor destroyed, but only transferred or transformed. Sorry, that was the law of conservation of energy. Law of conservation of mass states that matter can neither be created nor destroyed. And for all balanced equations, as I said, the mass of products has to equal the mass of reactants. So the mass of reactants has to always equal the mass of products. So that was the law of conservation of mass. Now let's go to a question, right? So always remember the mass of the reactants has to equal the mass of the products. So what is the mass of each reactant? So if we look at magnesium, look at oxygen, if we go back to the periodic table, oxygen should be 16 and magnesium should be 20 something, I think. And let's look at what is the mass of the product. So the product is 80.6. Now let's look at the total mass of reactants, right? So let's look at the total mass of reactants. So yeah, what is the mass of each reactant? Magnesium is 24.31. What is the total mass of reactants? We have 48.6 plus 32, which is 80.6. And so does the experimental data support the law of conservation of mass? Let's explain this, right? So let's look at this. Magnesium plus oxygen goes to magnesium oxide, right? 2 Mg plus O2 goes to 2 MgO. So in this case, this does support the law of conservation of mass, right? Because the mass of reactants, 80.6, equals the mass of products, which is 80.6 grams. So first, what I would do is I would just define the law of conservation of mass for this question. So the law of conservation of mass states that mass can neither be created nor destroyed, as per what said here. Mass can neither be created nor destroyed. And so I've defined the law of conservation of mass. And then according to the definition of the law of conservation of mass, as the mass of the products, which is as the mass of the reactant, which is 80.6, equals the mass of the products, the law of conservation, the experimental data supports the law of conservation of mass. And I would say that. And if you want to add even more, so depending on how many marks this is, so what I just answered would be a 2-mark version of this question. If there was even more marks, what I would do is I would write the chemical equation for this. So this one looks like, because it's 24.31, if we multiply this by 2, we get 48.6. So what this looks like is 2 Mg plus O2 goes into 2 MgO. So that's what that looks like, right? So I would draw out the chemical equation and I would link that to the masses itself to show that mathematically as well, the reactants of the mass of the reactants equals the mass of the products. So moving on. Now we go into 2.1.2. Relate stoichiometry to the law of conservation of mass in chemical reactions by investigating, balancing chemical equations, and solving problems regarding mass changes in chemical reactions. So let's go in. So stoichiometry is the study of quantitative ratios between chemical substances that undergo physical change or chemical change. So it's a ratio basically. So we can look at the coefficients here. The coefficients here is 2 and 2. So the stoichiometric ratio is 1:1 between H2 and H2O. So chemical equations are balanced by ensuring that there are the same number of atoms of each element on the left-hand side and the right-hand side. So now let's look at this equation, right? We have 2H2 plus O2 goes to 2H2O. So what we basically do is we count the number of each atom of each element on both sides. So how many hydrogen atoms are there? There's 2 times 2, so there's 4 hydrogens. How many hydrogen atoms are here? There's 2 times 2, which is 4. So the hydrogens are balanced. Let's look at the oxygens. How many oxygens are here? O2, that's 2. How many oxygens are on the right-hand side? We have O multiplied by 2, so that's 2. So is this equation balanced? Yes, because there's 4 hydrogens and 2 oxygens on the left-hand side and 4 hydrogens and 2 oxygens on the right-hand side. So this is what a balanced equation looks like. So let's look at how to balance chemical equations now. First, we write down the chemical equation. We determine the number of atoms per element present on both sides, and then we use a coefficient to balance a single element. And then we continue this for all atoms. So you want to find the lowest common multiple, basically. And then we check the number of atoms on the left and right-hand side to ensure that they are equal. So the method to this is to find the lowest common multiple. So let's look at this question, right? Look at an example. So we have CH4 plus 4Cl2 goes to CCl4 plus 4HCl. So let's check if it's balanced. So let's look at the first element, carbon. How many carbons are on both sides? 1. How many carbons are on the right-hand side? 1. So carbon is balanced. Let's look at the hydrogens now. How many hydrogens on the left-hand side? 1, 2, 3, 4. 4 hydrogens. How many hydrogens on the right-hand side? That's 1 times 4, 4. So hydrogen is balanced. Now let's look at chlorine, right? How many chlorines are present? So if we look at chlorine, we have 1, 2 times 4, 8. So 8 chlorines are present on the left-hand side. Now let's go to the right-hand side. How many chlorines are present? Well, there's 4 here, but that's not 8. Then if we go here, there's 1 times 4, 4. So we have 4 plus 4, that's equal to 8. So we have 1 carbon, 4 hydrogens, 8 chlorines, 1 carbon, 4 hydrogens, 8 chlorines. Is this a balanced equation? Yes, because the left-hand side has the same number of atoms of elements as the right-hand side. So now let's balance one of these following equations. So FeCl2 goes to FeCl3. So if we look at this, 1 Fe, 1 Fe, the ion is balanced. Now let's look at chlorine, right? Cl2, so 2 chlorines on here, 3 chlorines over here, so Cl2 isn't balanced. What we need to do is we need to balance it. So now we need to find the lowest common multiple between Cl2 and Cl3, or basically the lowest common multiple between 2 and 3, which is 6. So we need to have this side, the right-hand side, have 6 chlorines, and the left-hand side have 6 chlorines as well. So we'll multiply this entire compound by 2. So we have 2 FeCl3. So the number of chlorines is Cl3 times 2, which is 6 chlorines. So 2 FeCl3. So Cl2, how do we get that to be 6? We multiply this by 3. So 2 times 3 is 6, so there'll be 6 chlorines. How do we get this? How do we balance this now? There's 2 on this side, so we have 2 Fe. So what we have to do is add 2 Fe here. So 2 Fe plus 3 Cl2 goes into 2 FeCl3, or turns into 2 FeCl3. Does that make sense? Cool. So now we have iron oxide now, so Fe2O3. So let's look at this, right? Is iron balanced? No, iron is not balanced. So we know, so in my opinion, I probably shouldn't be balancing iron right now because iron is a lot easier to balance than oxygen. So I want to get the hard things out of the way first. That's kind of how you should look at this. So what's harder to balance? Oxygen. So let's look at oxygen, right? 2 to 3. The ratio is 2 to 3 again. So just like in the previous question, just like in part B, we need to balance that. Ratio is 2 to 3. We need to balance that. So I'll put a 3 in front of O2 to get 6 oxygens, and I'll put a 2 in front of O3 to get 6 oxygens on the right-hand side as well. So 3 here, 2 here. So I have a 3 in front, 3 here, 2 here. So 3 on O2, 3 O2, and 2 O3. So now on my right-hand side, I have 2 Fe2O3. So how many ions do I have? I have 2 times 2, that's 4. So I have 4 Fe on the right-hand side. So on my left-hand side, I'll put a 4 on this side. So 4 Fe plus 6 O2 goes into 2 Fe2O3, which is 4 Fe plus 6 O2, or 6O. So yeah, this side is balanced and this side is balanced. So that's how you balance part B. So part C, you do the same thing. You try and count which is there. So let's look at the answers right now. So 4 Fe plus 3O2 goes to 2 Fe2O3, as I said before. So now let's look at and 2 Fe plus 3 Cl2 goes into 2 FeCl3. So these are the answers for part A and part B. Now let's try and do part C. So part C has a lot more compounds, right? So let's look at this first. So we have SO4 over here, and we have SO4 So we have 3 SO4 compounds, right? When we're looking at these, like, SO4, PO4, those types of compounds, right? We don't want to break them up into sulfur and oxygen specifically. We just want to look at SO4 or PO4, this specific compound, as one atom, basically, or as one element, basically. So we're trying to balance this group itself. So there's 3 of these sulfate groups. Oh yeah, there's 3 of the sulfate groups. So what we do is we multiply this side, but we add a 3 on this side to account for this. So we added 3 on this side to account for the sulfate group. So now we have 3 H2SO4 instead of 1 H2SO4. So if I put a 3 on this side, and if I look here, right, we have iron, we have 2 ions, right? So I put a 2 on this side. So I have a 3 on this side, 2 on this side, right? And funny enough, that balances itself, because if we have 3, 2 here, we'd have 6 hydrogens and 6 bromines. So if we balance this now, HBr, we have to put 6 on this side. So if you look at this right now, I put 3 so that I can balance out the sulfate. So 3 over here, so I can balance out the sulfate. And then I have to balance out the ions. So I have 2 ions over here, so I added a 2 on this side. And then I have to balance the hydrogens and the bromines, right? Funny enough, I have 6 bromines on this side and 6 hydrogens on this side. So all I have to do is I have to add a 6 on the right-hand side to balance this all out. So that's how I would go around balancing the equations. So hydrogen is often the easiest one to balance, so I'd go through the hardest ones first. So this sulfate group, I balanced that first, then I balanced iron, and then it was a lot easier for me to balance hydrogen and bromine together. So that's kind of the thought process in terms of balancing equations there. So a couple hints now. So we adjust the coefficients, not the subscripts, right? So we don't, change SO4 to SO5. We adjust the coefficients, so from SO4 to 2SO4 or SO4 2. And if it's even to odd, then we multiply everything by 2 to make it all even. And we balance polyatomic ions as a whole. So if you look over here, the polyatomic ion is sulfate. So that's what I was saying. We consider this sulfate as like, one element basically. So we balance this polyatomic ion as a whole. So we don't split it up into sulfur and 4 oxygens. We consider SO4 as a whole. And then we also check the balanced equation afterwards to make sure that, we have the same number of atoms or polyatomic ions in both the right and left-hand side. So now moving on, we have a couple examples. So zinc sulfate plus oxygen goes into ZnO plus, or zinc oxide plus SO2. So if we look over here, right, we have how many oxygens on each side? So we have 2 and we have 3. So we have 2 on the left hand, 3 on the right hand. 1 S on both sides and 1 Z on both sides. So everything is balanced except for the oxygen. So now what we'll do is so O is even on the left and odd on the right. So what we do is we multiply it by 2 to make the O even. So we multiply 2 ZnO over here. So we multiply this by 2 so that now we have 4 oxygens on the right hand side opposed to 2 on the left hand side. So now we have 4. So now what we can do is we have 4 over here. So now what we can do is we can balance the Z and S and O. So because we have 2 Zn over here, what we can now do is we can multiply this by 2. So we get 2 Z and S. So we can balance the Zn and S now. But now by multiplying this by 2, so now I have 1, 2, 3, 4, 5, 6, right? So if I multiply the SO2 by 2 as well to account for this, now I have 6 oxygens on this hand side, right? To balance the 6 oxygens, I just multiply O2 by 3. So that's kind of the thought process. So I look at O is even on the left and odd on the right. So I multiply this side. So I multiply the right hand side to make the odd number an even number. And then I try and balance everything else. And then I fix it all by balancing out the oxygen finally. So looking at the second example now, I get lead nitrate plus sodium chloride goes to sodium nitrate plus lead chloride. So what I now do is I want to balance the nitrate as a whole, right? So I have 2 nitrates on this side and 1 on here. So to balance this out, I multiply sodium nitrate by 2 to account for the nitrates. Now they're all, so their nitrates even. So now what I need to do is I need to balance the sodium, right? So on the left-hand side, I have 1 sodium. On the right-hand side, I have 2 sodiums. So to balance that out, I multiply the sodium by 2. And now let's look at the entire equation. So I have 1 lead, 2 nitrates, 2 nitrates, 2 sodiums, 2 sodiums, 2 chlorines, 2 chlorines. So everything is balanced. That's all good. So that's kind of the process on how to balance equations. So now moving on. So stoichiometry so basically what we learned now is stoichiometry plus the law of conservation of mass, which states mass of reactants is equal to the mass of products, as mass can't be created or destroyed. So now let's look at a couple questions, right? So 63.1 grams of sodium metal reacts with 188 grams of solid iodine. Calculate the mass of sodium iodide produced, assuming that all reactants are used up. So if we're going to do this question, remember the law of conservation of mass. So what we do is we have 63.1 plus 188 is equal to 251.1. So all we're doing is we're adding things up, right? And we can get it to 4 significant figures because the lowest amount of significant figures present here is 4. So we give our answer to the lowest amount of significant figures, which is 4 significant figures. So our answer is in 251.1 grams. And yeah, so we'll learn about mole ratio later, but when we're adding, when we're trying to, for this question, we don't really care about what the reaction is. This question is just testing our understanding to see whether we understand that the products have the same mass as the reactants. So yeah, all we have to do is add up the mass of the reactants to get the mass of the products. Now, moving on, the mole concept. So in this part, students conduct a practical investigation to demonstrate and calculate the molar mass or mass of 1 mole of an element and a compound. They conduct an investigation to determine that chemicals react in simple whole number ratios by moles. And you explore the concept of the mole and relate this to Avogadro's constant to describe, calculate, and manipulate masses, chemical amounts, and numbers of particles in moles of elements and compounds. So this N value is equal to moles. So moles is equal to mass of the compound divided by the molar mass of the compound. The percentage composition calculations and empirical formula, and limiting reagent reactions. So let's go through this now. So explore the concept of the mole and relate this to Avogadro's constant to describe, calculate, and manipulate masses and chemical amounts and numbers of particles in moles of elements and compounds. N equals mass over molar mass. So N is the chemical amount in moles, M is mass in grams, MM is molar mass in grams per mole. So we should be able to, we should be able to calculate the moles of elements and compounds. We should be able to find the percentage composition calculations and also the empirical formula of stuff. And we should be able to complete and solve limiting reagent reactions. So what is a mole? So I was pretty confused about, learning about what a mole is as well, because, you have the picture of the animal mole and, this is different. So just like, a baker's dozen, so a mole is just like a unit of measurement, right? So we have like, we have a dozen, we have, what else do we have? We have a dozen, which is 12. We have, different words, basically, different words for units of measurement, right? So a dozen equals 12, just like how a dozen equals 12. A mole is equal to 6.022 times 10 to the power of 23 particles. So when we think about like, a solution, right? Because particles are so tiny, like 100 milliliters of some solution will have so many particles inside of it. So 1 mole is trying to simplify that, it's trying to simplify or give a simplified expression of how many particles are in there. So if I have 1 mole of water molecules in that water, I know that means I have 6.022 times 10 to the power of 23 particles of water in that solution or in that substance. I hope that kind of makes sense. And so 1 mole is the number of particles, basically. So the way they calculated this is 1 mole is the number of particles in 12 grams of carbon-12, which is used to define the mole. And everything is measured relative to this. So everything is measured relative to the number of particles in 12 grams of carbon-12. So that's the measurement. So 1 mole contains 6.022 times 10 to the 23 particles of that specific substance. And this 6.022 times 10 to the power of 23 is what's called Avogadro's constant. So yeah, it's called Avogadro's constant or Avogadro's constant, I guess. Yeah, it's a pretty funny meme. But yeah, this 6.022 times 10 to the power of 23 is what's called Avogadro's constant. So now let's look at the main equations that we'll be going through when we're talking about molar calculations. So we'll be looking at N is equal to the number of particles over 6.022 times 10 to the power of 23, which is Avogadro's constant. So this is the first equation, right? So what does this first equation mean? So now, if I have 2 moles, right? So let's say I have 2 moles of something, what that's going to look like is I'm going to have 12.044. So what I'll have is the number of particles, right? So something divided by 6.022 times 10 to the power of 23 has to equal 2, right? So 2 moles. So the number of particles I'm going to have is 12.044 times 10 to the power of 23. So if I want to find the number of particles, all I have to do is I'll have to multiply the amount of moles there by Avogadro's constant to find the total number of particles present. The next way to calculate the number of moles is if I have the mass of the substance and the molar mass of the substance, then I can find the moles of that substance as well. So mass, which is M, divided by molar mass, MM, is equal to moles. So molar mass is basically like, if you look at the chemical table, you'll see oxygen has a molar mass of 16, I think. So that's kind of what molar mass is. And if you look at this mm, it doesn't have to be denoted as mm. So some schools, they denote it as just capital M, but it's a lot easier, and I personally like denoting it as mm as well. So it's a lot easier that way. So yeah, the relationship between moles, mass, and Avogadro's number is defined by the following, where, moles is equal to the number of particles divided by Avogadro's constant. So let's look at this question. A sample contains 1.25 moles of NO2, or nitrogen dioxide. How many molecules are in the sample? So if we go back now, we're trying to find the number of molecules in this substance. So we are trying to find N. We know what Na is, and we know what N is. So what we do is we do N, or this number of particles, is equal to simple N multiplied by Avogadro's constant. So if we look at that chemically, what that looks like is N is equal, so we rearrange the equation to get N is equal to N times Na, and then we sub in the value. So Another important thing is, which is a lot more prominent in physics than in chemistry, when you're answering questions with, equations or stuff like this, right? Letters, basically like algebra. When you're doing algebra and you're trying to sub in values after you get to an equation. So say you're trying to do moles, right? N is equal to mass over molar mass. You don't want to sub in your equation straight away. So if you're trying to find molar mass, for example, you want to rearrange your equation with those algebraic terms, so with the letters in that equation. And then once you've rearranged the question to make your answer, to make what you're looking for the subject of that equation. So that's what we did here, right? We want n, and we made that the subject of the equation. We said n is equal to simple m times na, right? So we made n the subject of the equation. Once you've made n the subject of the equation, then you can sub all your numbers in, and that will make it a lot easier for you to lay out your answer and also get the correct answer. So you won't make any silly mistakes when you're writing the calculations out, missing one number and then getting the wrong answer. All you have to do is sub it in at the end, and then it's a lot easier and a lot cleaner to mark as well, and you're more likely to get the right answer. So in this case, we've rearranged the question. We have n is equal to n times Na. We have 1.25 moles times 6.02 times 10 to the power of 23 molecules per mole to get a total molecule number of 7.52 times 10 to the power of 23 molecules. So another thing is, after writing these questions, this is what I did personally for my HSC as well. After writing the question, I write a little sentence at the end that kind of like in English kind of answers the question. So I get this value of 7.52 times 10 to the power of 23 molecules. But to really answer the question, I say therefore. That's what the three dots are. These three dots in this orientation is a simplification of therefore. Therefore, there are 7.52 times 10 to the power of 23 molecules in 1.25 moles of NO2. So after doing the calculations, I then directly answer the question by saying there are this many molecules in NO2. So I don't leave this number, even though without this sentence, you'll probably get the mark. I don't leave this up for interpretation. I specify that there's this many molecules in this many moles of NO2, which is what the question is asking us for. So now let's look at the relationship between moles, mass, and molar mass in this following relationship. So moles is equal to mass over molar mass. And molar mass is the mass of 1 mole of an element. So 1 mole of oxygen should weigh 16 grams, because the molar mass of oxygen should be 16, if I'm correct. It would be very sad if I'm not correct. But yeah, for the molar mass of a compound, it's basically the sum of the molar masses of all elements in a compound. So if I want to find the molar mass of, let's say, SO2, or CO2, sorry, assuming that the molar mass of carbon should be around 12.01. So the molar mass of carbon dioxide is 12 plus 16 plus 16, which is 32 plus 12, which is 44. So 1 mole of carbon dioxide should weigh 44 grams. But yeah, so now moving on. So yeah, 16 plus 16, 32 plus 12, which is equal to 44. So yeah, 1 mole of carbon dioxide, which is CO2, should equal to 44 grams. Or the molar mass of carbon dioxide is 44 grams per mole, basically. So yeah. Now let's look at percentage composition to numerically express the percentage of a component in a substance. So percentage composition is percentage by mass of the element over the mass of the compound. So if I'm trying to find the percentage by mass composition of carbon in carbon dioxide, what I do is I look for the mass of the element, which is 12.01, over the mass of the compound, which is 12.01 plus 16, which is 44.01. So what I do is I do 12.01 over 44.01 times 100, and that would give me the percentage by mass, or percentage composition by mass of carbon in carbon dioxide. And we need to ensure that the units for the numerator and denominator are the same, but that should be okay, as the mass of the molar mass should be in the same units. So yeah, the empirical formula now displays the simplest ratio of the elements in a compound. So that's the difference between empirical and molecular formula. So empirical formula is also known as, or you could also call it, the ratio formula. So it shows the ratio of substances, of different elements in the substance. So we have the chemical formula C6H12O6. The empirical formula would be CH2O. So that shows the ratio of carbons to hydrogens in these different substances. So we have S2O2. Empirical formula for that is SO. We have C6H14. The empirical formula for that is C3H7, because we divided by 2, we divided by 2 here, and for this instance, we divided by 6. So yeah, empirical formula is the simplest ratio. It's basically the ratio formula, and that's what you need to know here. That's why a simple ratio is bolded in red. So yeah, now let's go through another question. So to calculate the empirical formula for substance, let's look at the following example. A 100-gram substance contains 38.7% carbon, 9.7% hydrogen, and 51.6% oxygen by weight. Work out the empirical formula. So we'll need to know the number of moles of this substance, right, to work out the empirical formula. So we can, if we multiply 38.7%, we'll get grams. So there's 38.7 grams of carbon. But to find out how many molecules that is, we'll have to find the ratio in moles, right? So now if we look at the answer, right, first we can find the mass of each substance. So 0.387 times 100 is equal to 38.7 grams. 0.097, which is 99.7%, times 100 equals 9.7 grams. And 0.516 times 100 is 51.6 grams. And then we can find the number of moles, because the number of moles is what allows us to write an empirical formula, but because that gives us the ratio of the number of particles within that compound, or within 100 grams, right? So now let's find the moles. So moles equals mass over molar mass. So 38.7 divided by 12.01 is 3.22. NH 9.7 divided by 1.008 is 9.62. And NO, which is 51.6 divided by 16, which is the molar mass, is equal to, so the moles of oxygen is equal to 3.23. So if we're doing this in a ratio now with an empirical formula, it will be 1 to 3 to 1. So yeah, let's look at the formula now. So the formula of the moles of carbon to hydrogen to oxygen is 3.22 to 9.62 to 3.23. So now if we divide all the numbers by 3.22, or approximately 3, so you don't need to divide it by 3.22, you just take an approximate, right? So if we take an approximate, the ratio is roughly 1 to 3 to 1, right? So the empirical formula will be 1 to 3 to 1. So CH3O. So that's how you would find the empirical formula. So what's very important is you can't just find mass. So mass doesn't give the empirical formula. It's not 30. So even though, it's 30, even though it's 51.6% oxygen, it's only one oxygen at the end, right? CH3O. And even though it's 9.7% hydrogen, there's 3 hydrogens in the entire thing, right? So you can't just use mass. You can't just use the mass to find the empirical formula. You need to use mass and then use that mass to find the moles and the ratio of the moles of the compounds, or moles of the atoms or elements in that compound, to find the empirical formula. So that's what you do there. Now, moving on. A student knows that a compound contains 32.65% sulfur, 65.3% oxygen, and 2.4% hydrogen by mass. What is the empirical formula of this compound? So, if we're comparing this question with the previous question, in the previous question, they give us a 100-gram substance, right? So we know that total mass is 100 grams. This time we don't. So how do we do this? The method, I'll tell you, is the same. We still need to find the mass, then convert that mass into moles, and then we find the ratio of moles, and then by finding the ratio of moles, we can find the empirical formula. So how do we find the mass? Well, it's actually quite simple. We just pretend like we take a 100-gram sample. So we'll take a 100-gram sample of this compound. And so by taking a 100-gram sample, the ratio should still be the same. So the ratio of moles within a 100-gram or a 102-gram sample should still be the same. So taking a 100-gram or a 200-gram sample, the ratio of moles should be the same, because the empirical formula should also be the same, right? So let's pretend that we take a 100-gram compound. So let's pretend like we take a 100-gram compound. It will contain 32.65 grams of sulfur, 65.3 grams of oxygen, and 2.04 grams of hydrogen by mass in a 100-gram sample, right? So what's the empirical formula of the compound? So let's assume the total mass of SOH is 100, so 32.5. So as I mentioned before, this is what I just mentioned. So now let's find the molar mass of each of them. So the molar mass of sulfur is 32.07, molar mass of oxygen is 16.00, and molar mass of hydrogen is 1.008. So now if we find the moles, or the ratio of moles, we get 1 to 4 to 2. Based by N equal to mass over molar mass, following this equation, we get a ratio of moles to 1 to 4 to 2 approximately. And so now, if we're trying to approximate the ratio is approximately 1 to 4 to 2. So by doing that, we get a ratio of 1 to 4 to 2. And so the empirical formula is S1O4 2H. So the empirical formula is H2SO4, which is, sulfuric acid. That is how you would find the empirical formula, and that is how you would answer a question like that. So now, moving on, let's look at limiting reagent questions. So the limiting reagent is the reactant that is consumed completely and thus limits the reaction. So within a reaction, right, you're going to have you're not going to have equal parts of everything, right? So sometimes based on the stoichiometry or the molar stoichiometry, one more thing is going to be required than another thing, right? So if we go back, let me just explain real quickly what I mean. So let's go back to one of our equations that we went through. So here, actually, even better. Let's look at, actually, let's go forward. Let's look at here, right? So for this question, right, we need 2 moles of sodium for every 1 mole of I2. So for every 1 mole of I2, we need 2 moles of sodium for a complete reaction to occur to get 2 moles of sodium iodide. So for every 2 moles of sodium, we need 1 mole of I2 or iodine to get 2 moles of sodium iodide. So that's how it works. So there's a stoichiometric ratio. So if I add 1 mole of I2, then I need to add 2 moles of sodium to completely react everything to get 2 moles of sodium iodide. If I only add 1 mole of sodium and 1 mole of iodide, then the limiting reagent will be sodium. So sodium is limiting the reaction, right? So because of that, I'll have 0.5 moles of I2 left over, and I'll only produce 1 mole of sodium iodide. If I add 1 mole of each, this reaction can't go to completion. And so, or this reaction won't, there'll be stuff left over after the reaction is over, and that stuff left over will be iodine because that's in excess now. And what I'll produce is 1 mole of sodium iodide. So going forward now, so the limiting reagent is a reaction that is consumed completely and limits the reaction. It's basically the substance that runs out first in a reaction. So once it runs out, then the other one stops reacting, and so the reaction stops. The excess reagent is a reactant that is left over. So in that case where I added 1 mole of sodium and 1 mole of iodine, I2 becomes the excess reagent and sodium becomes the limiting reagent. So let's look at this, right? When 8 grams of solid zinc and 35 milliliters of hydrochloric acid react, zinc chloride and hydrogen gas is produced. What is the mass of hydrogen gas produced? The density of hydrochloric acid is 1.15 grams per milliliter. So we can't use mass now, right? So now that we've learned about moles, we need to use moles to calculate the answer. So we need to turn these grams and these milliliters into moles, right? So we can do this with 8 grams. We need to divide it by the molar mass of zinc to find moles. For hydrochloric acid, we find the molar mass of this entire compound, and then we turn 35 milliliters into grams, right? So if there's a 1.15 grams per milliliter, we just need to, if there's 1.15 grams per milliliter, all we have to do is we have to multiply 35 by 1.15 to find the total grams of hydrochloric acid, and then we divide that by the molar mass of hydrochloric acid to find the moles. So first we write a balanced chemical equation. That's always important. Always write a balanced chemical equations for questions like this. So zinc plus 2 HCl equals zinc chloride and hydrogen gas. So if I'm balancing this now, so I have zinc chloride, I know I need 2 chlorines. So what I have to do is I have to put a 2 in front of HCl. And now because I have 2 hydrogens, I can write an H2. So everything is balanced pretty simply right there. Now we can calculate the mass of HCl using the density formula, as I mentioned before. So if I multiply by 1.15, I get 40.25 grams. So it's just, the denominators cancel out. There's no milliliters, there's only grams left over. 40.25 grams. And then I calculate the moles of the reactants using moles is equal to mass over molar mass. So 8 over 65.38, which is the molar mass of zinc, is equal to 0.122 moles. So there I have 0.122 moles of zinc. And now I found the molar mass of HCl this way. I have 1.104 moles of HCl. So let's calculate the limiting reagent using this, right? Let's see if there is a limiting reagent. So for every 2 moles of hydrochloric acid, I need 1 mole of zinc. So for every 1 mole of zinc, I need 2 moles of hydrochloric acid. Or for every 2 moles of hydrochloric acid, I need 1 mole of zinc. Or for every 1 mole of hydrochloric acid, I need half a mole of zinc, right? So they have a ratio of 1 to 2. Now let's go, right? So there's 1.104 moles, right? So for 1.104 moles of HCl, I need around 0.5 moles of zinc, right? A little bit more than 0.5 moles of zinc, around 0.55 moles of zinc. But how many moles do I have? I have 0.122. So what's the limiting reagent? Zinc. So zinc zinc would run out first, because to react all of the zinc molecules, all I need is 0.244 moles of hydrochloric acid. I just need twice the moles of zinc to react all of the zinc. So after 0.244 moles of hydrochloric acid is used, I'll have around 0.9 moles of hydrochloric acid left over. So HCl is the excess reagent, zinc is the limiting reagent. So to find the limiting reagent, we use the molar ratio. So the molar ratio of zinc with hydrochloric acid is 1 to 2, right? Because if we go over here, there's a stoichiometric ratio of 1 to 2. So that's the ratio, right, of moles as well, molar ratio. So that's 0.122. So 1 mole of zinc is needed for 1.104 moles of HCl. So 1 mole of zinc equals 0.122 moles. Yeah, so therefore 1 mole of zinc is 0.122 moles. 1 mole of zinc is needed for 1.02. So the amount of moles of zinc needed for 1.104 moles of HCl is 0.552, but we don't have 0.552. All we have is 0.122. So because zinc does not satisfy the amount of moles needed for a complete reaction as in a reaction that has no more leftover reactants, zinc is the limiting reagent. So that was the explanation that I talked about earlier. So we found what the limiting reagent is, we know what the excess reagent is, we know the amount of moles of each substance, and we know the chemical equation, but we haven't answered the question yet. We need to find the mass of hydrogen gas produced. So we need to find the mass of this. How do we do that? We can use molar ratios again, so 1 to 1. We can use molar ratios again to find the moles of hydrogen gas, and then multiply that by the molar mass to find the mass of hydrogen gas, right? Because N is equal to mass over molar mass. So now let's look at the stoichiometric ratios again. Or the molar ratios again. So what is the molar ratio between HCl and zinc chloride? The molar ratio is 2 to 1. So for every zinc chloride molecule produced, 2 moles, or for every 1 mole of zinc chloride produced, 2 moles of HCl are consumed. Or for every 2 moles of HCl that are consumed in the reaction, 1 mole of zinc chloride is produced. Same goes for hydrogen now. So for every 1 mole of hydrogen gas produced, 2 moles of hydrogen chloride is consumed. And for every 2 moles of hydrogen chloride consumed, 1 mole of hydrogen gas is produced. But now let's look at zinc. So for every 1 mole of zinc consumed, 1 mole of zinc chloride is produced. Same with every 1 mole of zinc chloride is produced, 1 mole of zinc is consumed. Now let's link zinc and hydrogen. For every 1 mole of zinc consumed, 1 mole of hydrogen is produced. And for every 1 mole of hydrogen gas is produced, 1 mole of zinc is consumed. So we have 2 different possibilities, right? We can use the hydrochloric acid molar ratio to find the moles of hydrogen gas, or we could use the zinc, molar ratio to find the formulation of hydrogen gas, or the molar mass, or the moles of hydrogen gas. Which one should we use? Well, we need to use the one with the limiting reagent, because that limiting reagent dictates how much is actually consumed, right? Because the other one is an excess, so we'd have to do more equations to find the leftover moles to compensate that. So it's just a lot easier to use the limiting reagent to find how many moles of H2 is produced. So if we go through now, we proved Zn is the limiting reagent. Now we need to find the mass of hydrogen produced. So we know Zn is the limiting reagent and then this is important because we always use the limiting reagent in our calculations. So the moles of H2 is equal to the moles of Zn because they have a 1 to 1 molar ratio. So the moles of H2 is also equal to 0.122. Now we use moles of a molar mass, so we multiply by 1.008 times 2 to get 0.25 grams. So obviously the significant figures would either be a little different or maybe stay the same, but because this question is for your understanding, the significant figures are relevant here, but in an exam question, make sure you round the question properly. And a lot of people, including myself in my class as well, got a question wrong where I looked at H2 and I only put 1.008 instead of multiplying it by 2. But that's wrong because we're considering the entire compound, right? We're not just looking at the moles of hydrogen, we're looking at the moles of H2. We're looking at the moles of 2 hydrogens, right? So we need to multiply 1.008 by 2 to find the total molar mass of that compound. That's a common pitfall as well. And so now we get a mass of 0.25 grams. So that's the limiting reagent aspect of our calculations. Now moving on. Yeah, so a little reminder is to always use the moles of our limiting reagent in our calculations. So now moving on, we can go to 2.2.1. Conduct a practical investigation to determine and calculate the molar mass of an element or compound. We've done that. 2.2.2, conduct an investigation to determine the chemicals react in simple whole number ratios by moles. Also done that. So these two syllabus are practical dot points, which we'll study more in depth at school. But for these, you use scientific equipment and follow method to obtain results. You'll get data which allows you to calculate the molar mass of something that you're measuring. And for dot point 2.2.2, you'll follow a similar procedure to draw results, and you'll use these results to determine the way chemicals react in simple whole numbers or whole ratios by moles. So it won't be too complicated. But yeah, now we'll move on to dot point 2.3, concentration and molarity. So the inquiry question here is, how are chemicals in solutions measured? So you might have experimented with some chemicals already, and in the labels in those bottles, you might have seen 1 molar or like 1 M, 1 capital M, right? So those that capital M is a unit that indicates the concentration of that liquid. And you obviously know that maybe you're only allowed to use 0.1 M substances because the other ones would be too dangerous. So the higher that molarity of that substance or higher the number of capital M, the greater the concentration is. So let's look at this. So in this dot point, we conduct practical investigations to determine the concentrations of solutions and investigate the different ways in which concentrations are measured. And then we also manipulate variables and solve problems to calculate concentration, mass, or volume, following C equals N over V. And we also do dilution, so the number of moles before dilution and the number of moles after dilution. And then we conduct an investigation. So this module is pretty investigation based to make a standard solution and perform a dilution. So yeah, we make a standard solution, we dilute it, and then you'll probably get questions on calculating the concentration after dilution. So yeah, now let's go to 2.3.2. Manipulate variables and solve problems to calculate concentration, mass, or volume using C equals N over V. So C is the unit for concentration, N is moles, V is volume. So C equals N over V, and then we use dilutions as well. So let's do this. So the concentration of a solution is the amount of solute in a given amount of solution. So how much solute is dissolved in that specific amount of solution. A concentrated solution has more solute, a diluted solution has less solute. So concentration is given by moles per volume, C equals to N over V. You might have noticed if a substance is concentrated or unconcentrated when you pour salt into water, right? So if we pour salt into water, we'll reach a point of saturation point, right? Saturation point is the point where no more of that solvent can dissolve in that volume. So our concentration is maximized. And you notice where you'll keep pouring salt, you'll keep mixing it to dissolve more salt in. And at some point, the salt just will stop dissolving and they'll just collect in the bottom, right? So when you've reached that point, the solution, the salt water, is saturated. No more salt can dissolve in that salt water. So at that point, concentration in that liquid is maximized. And we get that by C equals N over V. So now let's look at this. What is the molarity of 3.50 grams of NaCl in 230 milliliters of water? So look at the data that we have. We have mass and we have volume. Right, so our volume is 0.23 liters. So we have volume. Now to find concentration, we need moles, right? And we're only given grams. So can we turn grams into moles? Yes, we can. So we have moles is equal to mass over molar mass. We can use that to find. So do we know the molar mass? Yes, we do. Conduct the chemistry data sheet, the chemical table. You can use that to find the molar mass of NaCl, and we have the grams. So we have gram mass over molar mass is equal to moles. Using the moles, we can do moles over liters, and we can get the molarity of NaCl. So going through this, so 3.50 grams of NaCl times 1 over 58.4844, or basically 3.50 grams of NaCl divided by 58.44 is equal to 0.0599 moles. So what this equation is saying is we're dividing the mass of NaCl over the molar mass of NaCl to get 0.0599 moles. And now that we have the number of moles it has, we can divide that by the total volume, which is 0.23, to get a total concentration or molarity of 0.260 moles per liter. So this moles per liter value is also represented as a capital M, which is molarity. All right, moving on now. We can do dilution and molar ratios. So dilution lowers the concentration of a solution without changing the amount of solute. So basically what it does is, it lowers the concentration. So what we do is, let's say you add water in, right? So we add salt into that same amount of water. So we pour in 10 milliliters of water, and then we start pouring in salt into that 10 milliliter beaker of water, right? At a certain point, all the salt will have dissolved, and then the salt will start resting at the bottom, right? So we reach the saturation point, the solution is saturated. Now what we do is we add more water in. So we add another 10 milliliters of water in. So now the total volume is 20 milliliters with the same amount of salt in it. So now that solution has been diluted by a factor of 2, because now if we look at the fraction, right? We look at the fraction, the number of moles of NaCl, the number of moles of salt in that beaker of water is the same, but the volume has doubled, right? It's gone from 10 milliliters to 20 milliliters because I've added another 10 milliliters, right? So now the moles are the same, but the volume has doubled, so the concentration is halved. So we've diluted it by a factor of 2. So that's what we've done, right? So we add more solvent to it. So the dilution formula, they cannot change the number of moles of solute in the solution because we're not adding more substances in, we're only adding the solvent to it. So the solvent is what we're dissolving it in, the solute is what's being dissolved, right? So we're not adding more solute in it, we're adding more solvent. So the moles of solute stay the same. So yeah. Now we can, so N1 is equal to N2. That's what's very important in dilution. And now we have a new formula for moles, right? So we had moles is equal to, number of particles over Avogadro's constant. We also had moles is equal to mass over molar mass. Now, if we rearrange the value for concentration, so we multiply both sides by V, we get moles is equal to concentration times velocity. So moles is equal to CV. This is the main formula that we use to calculate dilution, because volume is what's changing, right? And concentration is changing as well. So if the moles are changing, we can find the change in concentration. If the moles are staying the same and volume is changing, we can find the change in concentration as well. So this is what we use. So starting concentration, starting volume is equal to final concentration times final volume, right? Because N, which is equal to CV, so N1 is equal to N2, so C1V1 is equal to C2V2, because the final moles and the initial moles and final moles are the same. So the starting concentration times starting volume has to equal the final concentration times final volume. So that's how that works. So now if we look at a question, a student conducting an experiment has 25 milliliters of sodium hydroxide solution of concentration 0.5 molarity, so 0.5 moles per liter, and he wants to dilute the solution to 0.26 moles per liter. How much water should he add? So he has 25 milliliters of solution, so the volume is 25 milliliters, right? So if we want to find the moles now, right? So we want to find the moles. So we want to break up this question. So we want to find the moles because the moles stay constant before and after, right? So to find the moles, we multiply C by V because, N is equal to CV. So we multiply C by V to get 0.5 times 0.25. So that's the amount of moles that we have. So let's look over here, right? So we multiply 0.5 by 0.025 liters to get 0.26 moles per liter times the velocity. So we get, so we use this equation, right? So we find the number of moles, initial moles, and now we need to find the amount of final moles, right? So what do we know about the final moles? The amount of final moles, what we know is we want to find that we know what the second concentration is, right? Because that's what we're trying to get to. So we know what C2 is. C2 is 0.26. So 0.5 times 0.025 is equal to 0.26, which is concentration 2 times the velocity 2. So velocity 2 dictates what the final velocity is, right? Not how much water we should add, but what the final velocity is. This is another common pitfall. A lot of people find velocity 2, which is 48 milliliters. All you do is we divide this by 0.26 to get 0.048. So a lot of people just leave it there. So what this says is the final volume must be 48 milliliters, not how much we already add, because we already have a volume of 25. So to find, because the question is asking how much we should add, to find how much we should add, we do 48 minus 25, which equals 23 milliliters. So we need to add 23 milliliters of water to the initial solution, to the concentration, to become 0.26 moles per liter. So that's how you answer that question. We use the formula C1V1 is equal to C2V2. Now, next question. 8.748 grams of magnesium hydroxide reacts with 280.0 milliliters of 1.000 moles of hydrochloric acid to produce magnesium chloride and water. Find the mass of magnesium chloride produced. So, first thing here is to write a chemical equation and write a balanced chemical equation. That's the first thing to do, right? So, we write a balanced chemical formula with the correct molar ratios because that's what we need for this question. So we have MgOH2 plus 2HCl goes to MgCl2 plus 2H2O. So this is the balanced chemical equation. Now we need to find the limiting reagent. We need to test to see if there is a limiting reagent because, there might not be or there might be. So we need to test to see if there is a limiting reagent. So the moles of magnesium hydroxide is mass over molar mass, which is equal to 8.748 divided by 58.326, which gives us moles of 0.149984. Yeah, just basically that amount of moles, right? If we look at here, the molar ratio is 1 to 2. So for this to be a complete reaction, hydrochloric acid should have 0.28-ish moles, right? So if we look at this now, hydrochloric acid has, to find the number of moles, we can do N equals CV. So by doing N equals CV, we get 0.28 times 1, which is equal to 0.28 moles. So this is approximately the same number of moles as magnesium chloride, but this is almost 0.15 moles, right? So we need approximately 0.30 moles of hydrochloric acid, right? Because this is almost 0.15. So we don't have enough hydrochloric acid to react with all of the magnesium hydroxide. So in this case, hydrochloric acid becomes a limiting reagent. So hydrochloric acid becomes a limiting reagent because we don't have enough, we're just barely short of the amount of moles of hydrochloric acid to completely react the magnesium chloride. So HCl becomes a limiting reagent and magnesium hydroxide becomes the excess reagent. So we have HCl in a 2 to 1, HCl is 0.28, magnesium chloride is 0.1499 something, so HCl becomes a limiting reagent. So for magnesium chloride, and so we find the moles of magnesium chloride now, we're finding the mass of magnesium chloride now. So magnesium chloride is the ratio of HCl to magnesium chloride is 2 to 1, right? So 2 HCl is 1 magnesium chloride. So the moles of HCl is 0.28. So we're using HCl once again because HCl is a limiting reagent. So there'll be excess magnesium chloride after everything is reacted. So we use HCl 0.28. And because the ratio is 2 to 1, if there's 0.28 moles of HCl, there's 0.14 moles of magnesium chloride. So now with that, we can find the mass of magnesium chloride by doing moles is equal to mass over molar mass. We can find the molar mass, 95.21 grams, using the chemistry periodic table. And we know what the moles are, so now all we have to do is multiply these two together to get mass. So mass is equal to 0.14 times 95.21, which equals 13.3294, which is approximately 13.33 grams. So we use the 4 significant figures because the lowest amount of significant figures in these questions is 4 significant figures. So we use 13.33 grams as our answer. So, dot point 2.3.1, conduct practical investigations to determine the concentrations of solutions and investigate the different ways in which concentrations are measured. We've done that. Conduct an investigation to make a standard solution and perform a dilution. So dilutions, we've done that as well. So again, those 2 dot points were sort of practical dot points, so you'll do them more in school. So you'll investigate concentrations and how concentrations are measured. You'll look at dilutions. You'll perform dilutions in class where you get a value, you dilute it, and then you keep diluting it multiple times. Then you test the concentration of that. That's pretty cool because you end up diluting it by a factor of 10 by the end of it. You also do standard solutions in class. So these are practical dot points which will be covered in lab sessions in class. So yeah, this is a visual representation of dilution. So if you look over here, this is obviously the most diluted. And as you keep diluting it, obviously the color becomes more faded as the amount of moles or the concentration of the subject becomes less and less. But the amount of moles in each of these are the same. So the moles is the amount of moles in each subject stay the same. Actually, for these two, they're different because you see how the volumes are the same. So the amount of moles, the amount of particles in here, the amount of particles present decrease, but the volume stays the same. So the concentration decreases as well. But yeah, so let's look at standard solutions. So standard solutions are solutions with a known concentration of a substance. So they have a known weight. So a known weight of solute is dissolved to make a volume. And they are used to determine concentrations of other substances through volumetric analysis. So we'll learn this in titrations in the HSC courses. Standard solutions are important, and we'll go into more detail in the HSC titration course. But yeah, basically what you need to know is they have a known concentration and a known weight of a pure solid, and so they don't have any imperfections or impurities, they're pure. So a known weight of pure solid is dissolved to make that volume of standard solution. And because we know their concentration, we use it to determine the concentration of other substances through a chemical process or like an experiment, basically, called titration. So yeah, this is what it looks like. We actually weigh out the mass of sodium carbonate, which is the primary standard, and we transfer sodium carbonate to a volumetric flask. We ensure complete transfer of sodium carbonate by washing the beaker with water to make sure all of it is rinsed out and transferred. Then we dissolve the sodium carbonate in water, and we add water to make the solution up to the calibrated mark. And so now we know the concentration of this standard solution over here. Now we can go through gas law. So how does the ideal gas law relate to all other gas laws? So in this dot point, we conduct investigations and solve problems to determine the relationship between the ideal gas law and Gay-Lussac's law, Boyle's law, Charles' law, and Avogadro's law. So let's go through this dot point. So the Kelvin temperature scale sets 0 degrees at absolute zero. So 0 degrees Kelvin is absolute zero. And this is the point where molecular energy is just non-existent, because they're all, so it's at a minimum, which is also nothing. So on a Celsius temperature scale, this is negative 273.15 degrees Celsius. So we can convert Celsius to degrees because they have the same increments by adding 273.15 to Kelvin. So 0 degrees Celsius is 273.15 degrees Kelvin. So yeah, this is kind of what it looks like. So 100 degrees Celsius is 100 plus 273.15 Kelvin, which is 373.15 degrees Kelvin. But yeah, so this is the ideal gas law. So PV equals nRT, and it's made up of a lot of different gas laws. So we have PV over T is equal to PV over T, P1 V1 over T1 is equal to P2 V2 over T2, P1 V1 is equal to P2 V2, V1 over N1 is equal to V2 over N2, V1 over T1 is equal to V2 over T2, P1 over T1 is equal to P2 over T2, a lot of different laws, right? So basically it means pressure times volume is equal to the number of moles times R, which is the gas constant, times temperature. So let's look at the ideal gases. So ideal gases are hypothetical gases whose molecules occupy negligible space. So they have no interactions and they obey gas laws exactly. So pressure, which is in pascals, times the volume is equal to the number of moles times the universal gas constant times temperature. So this universal gas constant is in your data sheet, so you don't have to worry too much about memorizing it. Now, there's a couple of different equations that when all combined together will make the ideal gas law. So let's look at the first one, Boyle's law. So Boyle's law states that for a given mass of gas at a constant temperature, the volume is inversely proportional to the pressure. So a quick heads up is that these definitions of gas laws, they could and most likely will be tested in your actual Module 2 exams. So you might want to pay attention and, maybe try and, as you go to school, maybe try and remember these definitions. So Boyle's law has a relationship between pressure and volume, which says that P1 V1 is equal to P2 V2. So pressure times volume initially is equal to pressure times volume after the change. So if I have a box of gas and I compress the box, so if I decrease the volume by a half, then the pressure will increase by a factor of 2. So it's that type of relationship. So volume is inversely proportional to pressure. So now we can go through Charles' law. So Charles' law states that the volume of a fixed amount of gas held at a constant pressure is directly proportional to its absolute temperature measured in Kelvin. So the relationship here is between volume and temperature. So because it's at a constant pressure just doesn't affect this equation because it's constant in both the left and right sections. So probably we don't need to care about pressure. We do need to care about volume and temperature though. So if we decrease the volume, if I decrease the volume, we increase, so let's look at it like this, right? So if I decrease the volume, right, what happens is I increase the pressure, right? So the volume of a fixed amount of gas held at a constant pressure is directly proportional to its absolute temperature measured in Kelvin, right? So say that I decrease V1, I decrease the temperature, so V1 is less, right? To account for V2 being less than V1, T2 will also be less than T1. So by the same factor. So if V2 is half of V1, then T2 is half of T1. because to allow for that ratio between volume and temperature to be the same before and afterwards. So that's what the equation is showing, and this is because there's a constant pressure between the before and after, before and after values. Now we have Guy-Lussac's law. So Guy-Lussac's law states that the pressure of a fixed amount of gas at fixed volume is directly proportional to its temperature. So this time, instead of a fixed pressure, it's fixed volume. And this is a relationship between temperature and pressure. This one's also a directly proportional temperature. So if a directly proportional relationship, so if I decrease pressure, I'll also decrease temperature because volume is constant. Now I have the combined gas law. So this is me combining Guy-Lussac's, Boyle's, and Charles' law to get P1V1 over T is equal to P2V2 over T. So yeah, in this one, I can say that, if I leave temperature the same, or let's say if I decrease the volume, right, I'll increase the pressure. And if I increase the pressure, right, particles are going to be colliding into one another more often. So the kinetic energy is going to increase. And so temperature will also probably increase. And we have Avogadro's law, and that states that equal volumes of all gases at the same temperature and pressure have the same number of molecules. So this is the relationship between the volume of the gas and the amount of substance in moles. So the moles will have to be the same regardless of volume, basically. That's what it's saying. All right, so this is like a quick summary of all the gas laws. So the ideal gas law is like all of the gas laws combined together. So the combined law, Guy-Lussac's law, Charles' law, Boyle's law, and Avogadro's law, all of them combine together to form the ideal gas law. So there's another simplification. For a given amount of gas at a constant temperature, the volume of a gas varies inversely with pressure. That's Boyle's law. Charles' law states that the volume of a fixed amount of gas is directly proportional to its Kelvin temperature if the pressure is kept constant. That's Charles' law. Guy-Lussac's law states that the pressure of a gas is directly proportional to the Kelvin temperature if the volume and amount of gas is kept constant. Then the combined gas law states that it combines Boyle's and Charles's and the temperature-pressure relationship into one equation. Each of these laws can be derived from this law. And then we have Avogadro's law, which is the pressure of the gas is directly proportional to the number of moles if the volume and temperature is kept constant. And then we have ideal gas law, which relates temperature, pressure, volume, and the amount of gas to the gas constant R, which is around 8.371, I think. But it's on your data sheet, so you don't have to worry too much. So now we enter our final questions of this lecture. At what temperature in degrees Celsius, so remember not Kelvin, degrees Celsius, our answer will be in Kelvin, not Celsius, so we need to convert it later. So what temperature in degrees Celsius does 48.5 grams of CO2 occupy 4.56 liters and a pressure of 2.5? So we have pressure, we have volume, and we have grams, which can be converted into moles, right? So we have P, V, N, and we need to find T, right? So what we do is we'll go back, we'll look at the equations. We're going to use ideal gas law, PV equals nRT, because we have R, we have T, we have V, we have P. R is on the data sheet, so you don't have to worry about it. We need to find T. We have nRPV, we need to find T. So let's rearrange this. So T is equal to PV over nR, and then we'll sub in the values and get it. So PV is equal to nRT. We'll find moles, which is equal to 1.10 moles, given by mass divided by molar mass. So we get 1.10 moles. We're trying to find T, right? So we'll do T is equal to 2.5 atmospheres times 4.56 liters over 1.10 times 0.0821 to get a temperature of 126 Kelvin. But we're not done yet. We need to turn it into Celsius. So what you do is you minus 273.15 from this to get the degrees in Kelvin, to get the degrees in Celsius. So yeah, that brings us to the end of our lecture. I really hope you enjoyed it.